Morning, Year 9. Today's lesson we're going to start looking at isotopes and nuclear reactions. So far in the course we've looked at atomic structure, including electrons, but I guess for this section here on isotopes, you can kind of forget about electrons for the time being. They are important, but really we're focusing on nuclear chemistry, what's happening in the nucleus, not as concerned about electrons at this point. So neutrons and protons, they're going to be your new best friend. That's what we're going to be focusing on for the next few lessons. So today's learning intention is to define isotopes to start with, and then hopefully we're able to determine atomic number, atomic mass, number of neutrons in different isotopes. So let's start with the basics here and just define what an isotope is. An isotope is an atom that has the same number of protons but a different number of neutrons. It has the same atomic number, which you find on the periodic table, but it's going to have a different mass number. Remember, your mass number is the number of neutrons and protons combined. So by definition, an isotope is the same element. Different number of neutrons means you're going to have a different mass number. Most atoms, they've got at least two naturally occurring isotopes. So scientists can make isotopes in the lab. Some of them are unstable and don't actually exist in nature, but you will usually find all elements will have at least two naturally occurring isotopes. But let's have a look at an example here, and we'll talk about these 3 dot points we just underlined here. We'll have a look at hydrogen as an example, just a simple one to start with. Normal hydrogen, so to speak, the most common type of hydrogen you'll find is hydrogen 1, we'll call it. It has a mass number of 1. We can write this out with our atomic notation. It actually becomes pretty handy understanding atomic notation when you're trying to differentiate between different isotopes. And I'll show you how we do that in a second here. But to start with, let's write hydrogen 1 with our atomic notation. So we start with the symbol, hydrogen, H. Atomic number, bottom left, is 1, and the mass number is 1. The mass number is just telling us that in hydrogen 1, we have 1 particle in the nucleus. And of course, that's got to be the single proton that makes up hydrogen. So let's have a look at hydrogen 2, which is an isotope of hydrogen. It has a mass number of 2, and you can see in the nucleus here, we have a neutron and a proton. So if we wrote this out in our atomic notation here, we'd still put our H here. Atomic number hasn't changed. If we start mucking around with the atomic number, we're going to change the element. And remember, an isotope is the same element. So that's a little cheat for you. It's always going to be the same atomic number on the bottom left there. What has changed is the mass number. We now have a neutron to go along with that 1 proton. So the mass number is going to be 2. Hydrogen 3, or tritium as it's known. Again, it's an isotope of hydrogen. Has the same number of protons, therefore it's hydrogen, but we now have 2 neutrons in the nucleus. So we can write this one out with our notation, H1, and a mass number of 3. So here we have 3 isotopes of hydrogen. And remember, an isotope, as we've just defined, same element, different number of neutrons. Now, to work out the number of neutrons in an atom, all we need to do is take the mass number and minus the atomic number. So we'll do a really simple example here. They'll get a little bit trickier later. But let's have a look at tritium, or hydrogen 3. Mass number is 3 minus 1 gives us 2 neutrons. And it's as simple as that. Okay, let's have a look at another example here. We have chlorine 35 and we have chlorine 37. So sometimes you'll hear people refer to uranium 235, uranium 238, carbon 13, carbon 14. What they're talking about are the different isotopes of those elements. So I'm talking here about chlorine 35 and chlorine 37. And the number here at the end basically is telling you what the mass number is. It's identifying the isotope we're talking about. So 75% of naturally occurring chlorine is the isotope chlorine 35, and 25% is chlorine 37. And let's have a look at how these two isotopes differ. So if you looked up on the periodic table, you'd find chlorine has 17 protons. So its atomic number is 17, which we have down here. 17 electrons, yeah, we don't really need to concern ourselves with electrons at the moment, but just remember, number of protons usually equals the number of electrons unless it's a charged atom or an ion. But let's just keep focusing on the protons and neutrons here. So 75% of chlorine is chlorine 35. We have 17 protons and we have 18 neutrons in the nucleus down here. There's 17 protons in there as well. So that gives us a mass number of 35. So if you have a look at chlorine 37, obviously if it's chlorine, this hasn't changed. We can't muck around with the number of protons or we change the element, but this has changed here. We have an extra 2 neutrons in chlorine 37. So two more neutrons in the nucleus here gives us a, well, if we add our 17 protons to that, we end up with our 37 here. So what we're looking at here, Year 9, we've got 2 isotopes of chlorine, chlorine 35, which is what we'd say the lighter isotope. It has less particles in its nucleus. The heavier isotope of chlorine, chlorine 37 on the right. The only thing that's changed here is the number of neutrons. So girls, remember that an isotope, it's an atom that has the same number of protons but a different number of neutrons. That by definition is what an isotope is. Alright, let's have a go at this one here. Now you'll notice that we've got, I'll just show you a bit of shorthand here to start with. We have this A and this Z at the bottom here. Now, one way to represent this atomic notation would be to say we have element X, whatever that happens to be, and its atomic number would represent as Z, and the mass number we would represent with a little a here. So really what this table is asking you to do, and I'm going to get you guys to have a go at this one now, is to determine, for starters, A, which will be our, if we have a look up here, A is our mass number, and this one here is Z, and we know that that is our atomic number. So what we're looking at then are 2 isotopes of uranium. We have uranium-235 on the left, uranium-238 on the right. This number hasn't changed. So what I want you to do is go ahead and work out, and remember one of our learning intentions is to work out the number of neutrons in different isotopes by using this information. Using this isotopic notation we have here, work out the number of neutrons and protons in this, well, these 2 isotopes here of uranium. And remember to work out your number of neutrons. It is mass number minus atomic number. So have a go at those. See if you can work out, well, for starters, what's the mass number of uranium-235? What's the atomic number of uranium-235? And once you've done that one, head over to uranium-238 and do the same thing here. What's the mass number of uranium-238? And what is the atomic number? And once you've done that for both of them, fill in here number of protons for both, and work out the number of neutrons for both of these isotopes. And here's your equation at the top. Mass number minus atomic number will give you number of neutrons. So have a go at that, and I'll put up the answers in a sec. So there we go. There's our answers. We have, well, starting with atomic number, that's an easy one. Remember, by definition, an isotope is the same element. The atomic number always is the smaller number here down the bottom left. So for both of them, the atomic number is 92. If we change that number, it's not going to be uranium anymore. So it has to be 92. The other easy one there is number of protons has to be 92 as well. That also defines the element that we're looking at. This is our mass number. So we put this into our top box down here. And then the last thing we need to do is work out the number of neutrons. So remember, it was mass number. So 230. So we'll do uranium 235. It was 235 minus 92, giving us 143 neutrons, which was the answer to this one here. Now you could do that same equation here and plug in, for uranium 238, and it'd be 238 minus 92 again, which gives us 146 neutrons. Or another way of looking at it is look at these two numbers up here. We've got 235 and 238. This number has gone up over here by 3. We have plus 3 in our mass number. So if our number of neutrons hasn't changed, we must have 92. The only thing that could increase this mass number here by 3 from 235 to 238 must have been 3 neutrons. And you can see that works out down here. So we've got 143 neutrons that we worked out from uranium 235. Uranium 238 has a plus 3 mass number, so therefore we must have 3 more neutrons. So that's a kind of a shorthand way of working that out. If you work out the first one, sometimes you can just look at how this mass number changes, and that'll indicate how many more or fewer neutrons that particular element has. Okay, have a go at these ones here, guys. Determine the number of neutrons in the following atoms. So we have carbon, it's what we call carbon 12. The second one we've got carbon 13. So carbon 13, that's also a stable isotope of carbon. We don't have it on here, but carbon 14 is the unstable isotope, so it decays. It's called a radioisotope. These two isotopes of carbon, though, carbon 12, carbon 13, they're stable isotopes. So not every isotope is radioactive. They're not all radioisotopes. So in this case here, what we're doing is determining the number of neutrons in the following atoms. If you have a look back at our learning intention, we need to determine the number of neutrons in different isotopes. So let's have a practice of this now. The last one down the bottom here is U238, which should look familiar to you. U238. All right, so maybe pause it here, have a go, work these ones out, and then I'll put up the answers. All right, carbon 12, mass number minus atomic number gives us 6 neutrons in a carbon 12 isotope. Carbon 13, our mass number 13 minus atomic number of 6 gives us 7 neutrons. So the only difference here between carbon 12 and carbon 13 is 1 more neutron in the nucleus in carbon 13. Uranium 238. Now we've already done this one, I just thought I'd throw it in there again, but we've got 238 minus 92. 238 minus 92. Remember, mass number minus atomic. So we work this out and we end up with 146 neutrons. It's a massive element, by the way, or atom, uranium. Very unstable. Use it in nuclear weapons, use it in nuclear reactors to provide us with power, but that is a massive atom, U-238, a huge nucleus, very unstable. So there we go. That's how we work out the number of neutrons in different isotopes. And you know what, while we're here, we should be able to determine atomic number. Now, if we look at isotope notation, it's the bottom left number down here. The smallest number is our atomic number. Our atomic mass, we're going to touch on that in a second on our next table. We're going to start filling out a bit of an activity. You guys will start looking at this atomic mass as we go ahead. All right, let's move ahead here. So what we'll get you to do is copy down this table into your book, and you're going to have to use your periodic table here, definitely. But in your workbook, copy down this table and see if you can fill it in. I'll go through a couple here just to give you an idea of what kind of information you need, where to find it, a couple of little things to keep in mind as you go. So I'm going to start with the top one here. Basically, in these columns, we have element name, atomic number, number of protons, number of neutrons, and then finally the mass number. So to start with carbon, we have a look on the periodic table. Carbon is in period 2, group 14. So we can have a look there on our periodic table. Pardon me. The atomic number is 6. So therefore it must have 6 protons. Number of neutrons. Well, we need to use the mass number given to us here to work out the number of neutrons. So if they've given us 12, number of neutrons will be mass number minus atomic number gives us 6 neutrons. So the number of neutrons here would be 6. And there you go. That's carbon. Have a look down here at hydrogen. You may find hydrogen listed twice. You might find other elements on this table that are listed twice. That's fine. You're just looking at different isotopes of the same element. So let's have a look at hydrogen. We've got 2 versions of hydrogen here. How are we going to work out which is which? I'm going to start with the top one here and have a look at hydrogen and go along to its mass number. So this is the clue that we're given. Mass number is 1. So that means it has 1 particle in its nucleus. It has to have a proton. So it must have 1 proton in the nucleus. If its mass number is 1, it would therefore have 0 neutrons. And being hydrogen with 1 proton, atomic number has to be 1. All right, so move down to the second hydrogen. It's the same element. It has to be the same atomic number. It has to have the same number of protons in its nucleus. This is different though. That is different though. We now have 2 neutrons. So what do you think our mass number is going to be? Remember, the mass number is the number of protons and neutrons combined, so this would be 3. So what we're looking at here is tritium, and if we put it into notation, we'd have H13. This hydrogen, the most common form of hydrogen, would be H11. Now, for this activity, you don't have to do these notations on the side here. I just drew them in just to show you what these elements or isotopes look like if we draw them with this isotopic notation here. Let's have a look at another one. Let's have a look down the bottom let's look at cesium down here. So the only thing that's given us for cesium is the number of neutrons. So let's start working out, based on our periodic table, what can we work out to start with? So atomic numbers, well, that's fairly straightforward. Cesium is in group 1, period 6. So we have an atomic number there. Let's have a look, 55. Atomic number of 55. By definition, that means we've got 55 protons in the nucleus. It's given us number of neutrons, so we're looking at 82 here. Remember the mass number of protons and neutrons combined. Add those 2 together. 137 is what we end up with here. So this is actually, this version of cesium down here, this isotope, this is actually a radioisotope, which means it's unstable. Radioisotope. It's unstable and will undergo decay. Now, decay is something we're going to talk about in the lessons coming up, but just for interest's sake, this version of cesium, this isotope of cesium, the number of neutrons in its nucleus causes this one to be unstable and decay. It's radioactive, and we call that a radioisotope. So, like I said, put down the rest of this table in your book and use your periodic table to work out the rest of this table here. You might have to find out what the element name is based on the information given. But rest assured, it doesn't matter which row you're working on, there's enough information in there, and it doesn't matter what information you're given, there's enough in there to be able to work out the other columns in that row. So see how you go with that activity to start with. Once you finish that, so pause it now, I guess, finish this table, and then once you finish that, you can move ahead.